Hello, viewer. Hello, good morning. Hello. Hello. I'm going to wait for at least 15 people before I get started. Howdy. Waiting for a few more people to join up. Good morning. My morning is going well. There's something very sad happening here, which is the cat that I'm watching has a swollen leg. So he's been limping around for the past few days. And yesterday he went to the vet and he got a splint on his leg and a cone. And it's really pathetic. He can't move very fast. But the nice thing is that he's sort of dependent on me, which is, um, you know, the cat does not really like me if he's healthy. But then now that he's not healthy, he's kind of like laying next to me and needs me to hand feed him and stuff like that. So it's kind of sweet. It's sad, but it's cute. All right, I'm gonna wait one more minute and then I'll get started. Okay. So one thing I wanted to talk about just really briefly is I wanted to tell everyone to join the Remind if you haven't already. You can find the join code for the Remind on the Canvas page, and then you click syllabus, and it's in the syllabus the number you have to text to, or the thing you have to text to join the Remind. So on the Remind, it's sometimes buenos dias. Sometimes I have to change my office hours for various reasons. So, I'll make an announcement on the Remind that my office hours had moved to this time. And so I think that on Monday and Tuesday, some people didn't get my message and they came to my office hours, but I wasn't there. So, yeah, just join the Remind and you can get an update if I have to change my schedule for some reason. What was the other thing? Guten Morgen. I know there was another thing, but I'm blanking on it. I can't remember what it is. It'll come to me later. All right. So what we're going to be doing today is kinematics equation problems. Okay. So it should be a fairly straightforward lesson. And I'm going to try to keep this a little bit shorter than usual because today's quiz has more questions than usual. So let me switch to the document camera. Okay. So last time we learned three really important equations. Okay. It's delta x equals v naught t plus 1/2 a t squared. Let me see if I can autofocus this a little bit better. We learned the equation v final equals v initial plus a t. And then we learned the equation v final squared equals v initial squared plus 2a delta x. Okay? And so these are called the kinematics equations. And in order to use these equations, you must have a constant acceleration. If you do not have a constant acceleration, then these equations are not true. Okay? So constant acceleration that is the condition in order to be able to use these equations. Now, it just so happens that pretty much for this entire course, we are going to be dealing with constant acceleration. So these equations are valid for pretty much the entire course. Okay? And so when you're choosing which equation to use, you want to notice that each equation has 4 different variables in it. And so when you have a problem, 3 pieces of information will be given. And then the 4th is what you're trying to solve for. And so you choose your equation based on that. And then you plug in the numbers and you solve the resulting equation. Okay? So today is just all about examples of using these kinematics equations. So as our first example, let's suppose you have a rocket. A rocket can accelerate at 30 meters per second squared, okay, when it fires its thrusters. How much time must it be fired for in order to increase the velocity from 1,000 meters per second to 2,200 meters per second? Okay, so this is a common, anyone play Kerbal Space Program? Put it into the live chat if you play Kerbal Space Program. If you haven't played Kerbal Space Program, I'm going to type it in the live chat myself just because this is an excellent game to learn about physics. If you have $20 lying around, or I don't know how much it is. I think it's $20 or $30. Great computer game. I should actually live stream it sometime because I have it on this computer. It might overload my computer, but I could try live streaming it sometime when we get to the appropriate unit. But it's teaches you a lot about physics if you play this game. And one of the things you do in the game is you can press a button and the rocket starts firing, and then you press the button again and it stops firing. And depending on how long you fire the rocket for, you build up more and more speed, or you run out of fuel. One of those two things is going to happen. Okay, so I find it's helpful to just do a little list of what are the knowns and what is the unknown. Okay, so the rocket can accelerate at 30 meters per second squared. Okay, so so that means that the acceleration is 30 meters per second squared. So that's A. And it says how much time must it be fired for. So that's saying that time is the unknown. Okay. And then it says we're increasing the velocity from 1,000 meters per second to 2,200 meters per second. So that means that V initial is 1,000 and V final is 2,200. Okay, so type it into the live chat if you know what the equation that we're going to use is. Which of these three are we going to use? And while I'm waiting for you guys to do that, I'm going to write the next example. Oh, that was fast. Okay. I have low delay this morning. Yes, you are all correct. It is the second equation. V final equals V initial plus AT. All right. So the V final is 2,200. The V initial is 1,000. The acceleration is 30. And the time is unknown, so we just leave that as t. All right. So now we just have a linear equation. So I subtract 1,000 from both sides. We get 1,200 equals 30t. Then I divide both sides by 30, and I get 40 seconds is the time that the thrusters would have to be fired for. Very good. Okay. So this is how that works. So you want to write down the knowns and the unknowns, choose an equation based on that, plug in the numbers, solve the equation. Let's do another. How about let's suppose that a sled. You ever go sledding? If you've ever been sledding before, which maybe you haven't because you're living in California, but I grew up in Washington State, so sledding was fairly common in the winter. And you sled, you go down a hill, and then at the bottom of the hill it levels out, and you kind of slow to a stop. Okay. So let's say a sled gets to the bottom of a hill. Traveling at 15 meters per second. So it gets to the bottom of the hill and it's coasting along the flat portion at the bottom of the hill, so it's going to slow to a stop. Okay. It slows to a stop. And let's say it goes forward 10 meters while slowing to a stop. So that was its stopping distance, was 10 meters. What was the acceleration? Of the sled. Okay, so I'm going to write down the knowns and the unknown. Okay. So the knowns are that the initial velocity is 15 meters per second. Okay. The final velocity is 0 meters per second. So notice how nowhere does it say the final velocity is 0 explicitly. It just says it slows to a stop. So you are going to you're going to simply read that sentence, and you're going to know that the final velocity is 0. We know that it does so in 10 meters. That's not an amount of time, that's an amount of distance, okay? So it gets to the bottom of the hill, it goes, and then once it's at the bottom of the hill, that distance, 10 meters. So delta x is 10 meters, and we want to know what was the acceleration. Okay, technically this is going to be a deceleration or a slowing down, and we'll see how that shows up in the math. So which equation am I going to use? One, two, or three? Equation 3, excellent. Equation 3. V final squared equals V initial squared plus 2a delta x. V final is 0. Okay. V initial is 15. 2 times a times 10. And so that, I'm just going to fast forward through the algebra. We have a equals minus 15 squared over 20. Yeah, which is negative 11.25 meters per second squared. So the fact that it was slowing down is represented by the acceleration being negative. Okay? You do have to be careful, though, because your acceleration, a negative acceleration does not always mean that you are slowing down, and that's really confusing. If your velocity is, what a negative acceleration means is that your velocity is becoming more negative, okay? So if you have a positive velocity and a negative acceleration, then that means that your velocity is going from 10 to 9 to 8 to 7, so you're slowing down, okay? But if you have a negative velocity and a negative acceleration, you're actually speeding up because your velocity is going from negative 10 to negative 11 to negative 12 to negative 13. So if the acceleration and the velocity have the same sign, if they're both in the same direction, then that means you're speeding up. But if they're in the if they have opposite signs, where one is positive and the other is negative, then you are slowing down. Okay, so that's a little bit tricky. It's just a little bit more subtle than it appears at first sight. So a negative acceleration does not necessarily mean that you are slowing down. In this case, it does, because the sled is moving in the positive direction at the bottom of the hill. One other little subtlety there I wanted to discuss is if we wanted to analyze this problem from the top of the hill, so when the sled is going down the hill, if we wanted to analyze this problem from the top of the hill to where it stops at the bottom, we could not use the kinematics equations. Why is that? That is because you have one acceleration while you are moving down the hill, and you have another acceleration when you reach the bottom and you slow to a stop. Okay? Right? When you're going down the hill, you're actually speeding up, and when you get to the bottom, you're slowing down. So you have two different accelerations. So who can tell me, why does that mean we cannot use these three equations? All right? Someone type it into the live chat, and I'm going to flip the page here. All right. These require constant acceleration. Yes, very good. So, so actually, if you wanted to, and this is what these are the kinds of problems we do in AP Physics C, where you have a constant acceleration for going down the hill, and then you have a constant acceleration for when you get to the bottom of the hill. So you could actually use these equations twice. You could use these equations for just the portion of the motion that is going down, and then just the portion where it is going horizontally. So it is possible to still use those equations, but it's just a little bit more subtle. Okay. So it turns out, so here's our sort of key new fact for today. Gravity causes a constant acceleration. Okay? The acceleration due to gravity is a constant acceleration. Okay? So the value of that acceleration is called g. And the value of the gravitational acceleration depends on where you are. So it's not necessarily perfectly constant, but for all intents and purposes, it's constant. But sort of the global average for the gravitational acceleration is 9.81 meters per second squared. Okay? Give me one moment. I'm going to turn off this my alarm that I forgot to. Okay, so 9.81 meters per second squared. Okay, so we will approximate that. So for every quiz problem, homework problem, IB exam, everything, you can approximate g, the acceleration due to gravity, as 10 meters per second squared. Okay? So for all the homework, you are going to use g equals 10 meters per second squared, not 9.81. The reason is that it's just easier to remember. Okay? So, we'll just use it as 10. And that's standard. If you use g equals 10 on the IB exam, you're good to go. Okay? So this is called the acceleration due to gravity. So if there's a problem where something is thrown through the air on Earth, okay? By the way, this is gravity causes a constant acceleration on Earth. Each planet has its own gravitational acceleration, okay? So for example, the moon, so g on the moon is 1.6 meters per second squared. It's about 1/6 what it is on Earth. So that means that things fall more slowly. On Mars, g is 3.7 meters per second squared. Okay. On Jupiter, Jupiter is a really massive planet, so its gravity is quite a bit larger. It's about 20 meters per second squared. Okay. Later on in this class, we'll actually learn how to calculate the acceleration due to gravity, if you know information about the planet. But yeah, we're going to mostly be doing problems where it's on Earth. Okay. So let me give you an example. You drop a tennis ball. You drop a tennis ball from, let's say, 45 meters high. How much time does it take to hit the ground? Okay, so we're assuming that you're dropping this tennis ball on Earth, okay? So what do we have here? So we've got, if you drop a tennis ball, what does that mean? Drop versus or release would be a synonym versus throw something. Well, if you are dropping a tennis ball, you are giving it an initial velocity of 0. Okay. The acceleration is going to be the gravitational acceleration. Okay, but there's one little twist I'm going to put in there. This is the magnitude of the gravitational acceleration, but gravity actually points downward. So we're going to call that an acceleration of -10 meters per second squared because gravity is going downward. Okay. How much time does it take to hit the ground? So that says time equals question mark. And then we are told that it's a 45-meter high building. Okay, so it goes from a y-coordinate of plus 45 to a y-coordinate of 0. So that's actually a negative displacement. So I'm going to call it delta y just because we're moving vertically. We're dropping something vertically. So delta y equals -45 meters. So which kinematics equation would we use for this? Someone tell me. While I type up the next, or while I write up the next example. Equation 1, yes. So we have delta y equals v naught t plus 1/2 at squared. V naught is 0, so this term goes away. Delta y is -45. The acceleration is -10, so 1/2 of -10 is -5. Okay. Notice how the importance of these two both being negative, because watch what's going to happen. We divide these two and we get 9 equals t squared. What if we forgot one of them? What if we said one of them was positive and one of them was negative? In that case, we would, when we divide, the negatives wouldn't cancel out. And so we would have -9 equals t squared. We take the square root, we get an imaginary number. Okay? Time is not imaginary, I assure you. So taking the square root, we get t equals 3 seconds. Very good. All right. Do you guys know what Old Faithful is? Old Faithful, the geyser. Let's just say Old Faithful erupts, spraying water let's say 130 meters into the air. I've never seen Old Faithful in person, so I don't know how high the column of water actually is. That's probably way too high, but you know, that's fine. What is the speed of the water exiting the geyser? Okay, so we have that delta y is 130. We want to get what is the speed of the water exiting the geyser. So that's the beginning of this water as it erupts. So we want to know what is v initial. We know that the acceleration is gravity, so the acceleration is -10 meters per second squared. And we need one more piece of information, okay? And this is This one is a little bit tricky, okay? So what we're going to consider, so we have this geyser erupting, right? So the geyser is going like this. There's the water. Water is spraying up into the air, like so. So the initial point is right here, and the final point is right here at the highest point, okay? Now the question is, what is the velocity at the highest point? And it turns out that the velocity is going to be 0 at the highest point. So why is that? What would it mean if you were at the highest point and the velocity was not 0? What if the velocity was positive at the highest point? Well, that would mean if you waited just a little bit longer, you would go higher, right? If the velocity was negative at the highest point, then that would mean just a moment before that you were up higher because you came down from a higher location, okay? So the highest point, you have final velocity of 0, okay? So this is the third kinematics equation. V final squared equals V initial squared plus 2a delta y. 0 squared equals V initial squared plus 2 times negative 10 times delta y. Oh, times 130, excuse me. And so basically that says that V initial equals the square root of 2,600. Which is about 51 meters per second. All right. I'm going to do one more example, and then we'll switch over to Zoom. By the way, what are we neglecting in using these equations by saying that the acceleration is just 10 meters per second squared? There's one thing that's really important in real life that we are sort of neglecting here. Type it into the live chat if you think you know what it is. Okay. Yeah, excellent. Air resistance. So air resistance is something that changes the acceleration from 10 meters per second squared. Also known as drag, yeah. So these equations are sort of approximation, like they're a first approximation to what is really going to happen. And it's a pretty good approximation unless you have something that's going really, really fast, okay? Because the faster something goes, the more drag it has. And so that is going to make the acceleration be more and more different from gravity. A place where these equations will work really well is the moon, okay? Because the moon has no atmosphere. So it has no drag. So there's nothing to modify the acceleration from the 1.6 meters per second squared. Okay. It would also work pretty well on Mars because Mars has a very tenuous atmosphere. The atmospheric pressure on Mars is way less than what it is on Earth. So there's just not as much drag. There is drag on Mars, but it's just much less. Okay, so I wanted to point that out. If you take my AP Physics C/IB Physics HL, we learn how to handle air resistance. Okay. All right, so this last example for today. So I'm going to make a drawing here. Okay. Okay. Um, all right. Cool. So your friend chokes on a chicken wing. So you give them the Heimlich maneuver, but with your foot. And so that causes the chicken wing. So you're laying on your back. Your friend gives you the Heimlich maneuver. You're laying on your back. You cough the chicken wing directly up into the air. Okay? So the initial velocity of the chicken wing is, let's say, 35 meters per second. That's totally not realistic because that's about 70 miles per hour. So that would mean you really gave, your body might explode if there was enough pressure inside you to launch a chicken wing at 70 miles per hour out of your mouth. But just making up numbers. So the chicken wing is, of course, going to fly through the air. It's going to go up, it's going to come back down, and it's going to hit you in the face. Okay? So my question is, how much time after the maneuver until wing returns? Okay? So we're asking for the time. Okay. We know that the initial velocity is 35 meters per second. We know that the acceleration is negative 10 meters per second squared. So there's one more piece of information, and this is kind of tricky. Okay. So the chicken wing goes up and it comes back down. So some of you might think that the final velocity is 0. Okay. But that is actually, while it is true, the chicken wing lands on your forehead or whatever, and it's just sitting there. But once the chicken wing lands on your forehead, its acceleration changed, which invalidated the kinematics equations, right? So really, what we're doing, the final velocity is not 0. What we're calculating is the moment, how much time just before it makes contact with your forehead, okay? And the final velocity is not 0 in that case, right? If the chicken wing had a final velocity of 0 just before it hit your forehead, then it would be levitating above your face, right? So, so we do not use v final equals 0. What we actually, you could use, so there's a comment in the chat that you could use v final equals minus 35. Because the speed that it goes up with is the speed. But we haven't really proved that. We haven't proved that the speed that something goes up with is the speed it comes down at. So I wouldn't necessarily use that piece of information, although it is true. We didn't prove that. But one thing we can say for sure is that the chicken wing starts at the elevation of your face, it goes up, it comes back down, and it ends at the elevation of your face. So the starting elevation is the same as the ending elevation. So that means that delta y is 0. Okay? So I prefer that to saying the final velocity is 0 meters per second. So the equation we're going to use is delta y equals v naught t plus 1/2 at squared. Okay, delta y is 0. V initial is 35. All right, so I'm going to add 5t squared to both sides. Going to divide both sides by 5. So we get t squared equals 7t. So at this point, we're going to divide both sides by t. Okay. Why can I divide by t? Well, you can't divide by a number if it's equal to 0. Okay. So we're dividing by t, and t is not equal to 0. So we can do that. All right. It's not an infinitely fast chicken wing that takes 0 seconds to get coughed up and then hit your face. So we have t equals 7 seconds. All right. So that is my lesson for today. I will meet you in the Zoom room.